And now in this lecture, we'll answer two questions. In the first question, we find out the area of this octagon ABCD that blocks this circle. And in the second question, we find out the area of this trapezoid ABCD. So we start with the first question. In the drawing, we have trapezoid ABCD. This trapezoid ABC. In the drawing, we have rectangle ABCD. Rectangle ABC blocks this circle. On this circle is described by rectangle ABCD. In addition, we know that this is called EF, this is equals to 12 units in its length. This is line segment FG, this is equals to 10 units. And our mission is to find out the area of this rectangle ABCD. So first of all, we know that all the angles inside the rectangle are right angles. So those four angles are all right angles. So this is also a right angle. So the ABCD is a rectangle. What is the area of any rectangle? The area of any rectangle equals to the length of the rectangle times the width. So we define the length of this rectangle ABCD as AB. And we define the width of this rectangle ABCD as AD. So just have to find out the values of AD and AB, and we will multiply them by each other, and this will be the result. The result will be the area of this rectangle ABCD. Okay. The center of this circle, when you find the center of this circle, this point is point O. When you join points O, point M is the point of tendency of DC with this circle. Point E is the point of tendency of tangent DA with this circle. And finally, point N is the point of tendency of tangent AB with this circle. So the next step, we join points O and M together by a straight line. And we define the radius of this circle as R. Point M is the center of the circle. Point O is the center of this circle. Point M is the point on the circle itself. Therefore, OM is the radius of this circle that is equals to R. According to our definition. The radius OM that is equals to R, the radius OM is drawn to point M, that is the point of tendency. Of tangent DC with this circle. And whenever your radius is drawn to the point of tendency, then tangent DC will be perpendicular to the radius MO. If DC is perpendicular to MO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and N together with a straight line. ON is of course the radius of this circle that is equals to R. The radius ON is equals to R. The radius ON is drawn to point N, that is the point of tendency of tangent AB with this circle. And whenever your radius is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. If AB is perpendicular to NO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. In the next step, we join points O and D together by a straight line. MOE is of course the radius of this circle that is equal to R. The radius OE is known to point E, that is the point of tendency of tangent DA with this circle. Whenever your radius is known to the point of tendency, then tangent DA will be perpendicular to the radius EO. If DA is perpendicular to EO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to the same rule, rule 1. By doing this construction, we get the small quadrilateral DMOE. Inside the small quadrilateral DMOE, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth pieces again, in total they must be equal to 460 degrees, according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth pieces angle must be equal to 90 degrees in its size. And the next step we focus on the lower quadrilateral EO and A. Inside the lower quadrilateral EO and A, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth pieces angle, in total it must be equal to 360 degrees. According to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth pieces angle must be equal to 90 degrees in its size. So if you found out that the big angle MON is equal to 90 degrees plus 90 degrees, that is 180 degrees. So the size of the big angle MON is 180 degrees. So it is on. The big angle MON is equal to 180 degrees in its side. And you know that any angle that is equal to 180 degrees in its size, it is defined as a straight line. So therefore, line segment MON is a straight line. If line segment MON is a straight line, then MN is also a straight line. So MN is a straight line that touches the circle at 2 points, point M and point N. And therefore MN is a chord. MN is a chord. MN is a chord. But MN is a chord that passes through point O, that is the center of the circle, and we know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore, MN is the diameter of the circle. MN is a chord that passes through point O. That is the diameter of the circle, and therefore point O that is the center of the circle, and therefore any chord that passes through the center of the circle is defined as a diameter. Therefore MN is the diameter of the circle. So it is here that MN is the diameter of the circle. MN is a diameter, it is absolutely a straight line, and therefore this shape DMNA is a quadrilateral because it has 4 sides, 1, 2, 3, 4. Okay, shape DMNA is a quadrilateral. What is it known? Shape DMNA is a quadrilateral. A quadrilateral with 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be at least a rectangle in front of the square. So we go to this big quadrilateral DMNA is a rectangle because it has 4 right angles. Therefore, quadrilateral DMNA is a rectangle according to rule 5. So it is on the big quadrilateral DMNA is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle DMNA, side MN must be equal to the opposite side DA. So in rectangle DMNA, side MN must be equal to the opposite side DA. But according to the definition, DA is the width of rectangle ABCD, so can I tell that DA is the width of rectangle ABCD? Okay. In the next step, we'll extend the radius EO of this circle by a straight line until it touches the circle at this point. Until it touches the circle. And we'll define the touching point of the extended radius EO with this circle, this point, as point L. EO is the radius, that is absolutely a straight line. We extended the radius EO by straight line. The result EL must be also a straight line because when you extend the straight line by straight line, the result must be a straight line. Therefore, EL is a straight line that touches the circle with 2 points E and L, and EL definitely passes from point O, that is the center of the circle, and we know that any chord that passes from the center of the circle must be the diameter of the circle. Therefore, EL is the diameter of the circle. EL passes from point O because we extended the radius EO by straight line. EO definitely touches point O, and we extended EO by straight line. Therefore, EL also passes through point O. So in total, we found out that EL is the diameter of the circle. So EL is the diameter of the circle. And we have already found out that MN is the diameter of the circle. So we can write here that MN is the diameter of the circle. So let's again. MN equals to DA equals to the width, and MN is the diameter of the circle according to what we have already found out. We just right now found out that EL is also the diameter of the circle. So we can write here that EL is the diameter of the circle. EL is the diameter of the circle, and from this long equation, EL equals to the diameter equals to MN equals to DA equals to the width. We know that EL is also the width of rectangle ABCD. EL is the width of rectangle ABCD. In the next step, so here we found out that EL is the diameter of the circle, so I write it down. EL is the diameter of the circle. In the next step, we'll join points L and F together by a straight line. By joining points L and F, we can get here peripheral angle LFE. Peripheral angle LFE subtends on EL, that is the diameter of the circle. We know that any peripheral angle that subtends on the diameter of the circle must be equal to 90 degrees in its size, according to rule 7. So I put quickly on rule 7. According to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees in its size. So here we have a circle. AB is the diameter of this circle. This is peripheral angle ACB that subtends on AB, that is the diameter of this circle. And according to this rule 7, peripheral angle ACB must be equal to 90 degrees in its size because it subtends on the diameter of the circle. So as I already mentioned before, we can implement rule 7 in our drawing. Why? Because in our drawing we have peripheral angle LFE that subtends on LE, that is the diameter of this circle. Therefore, according to rule 7, peripheral angle LFE must be equal to 90 degrees in its size. So in the right triangle LFE, we'll define this angle as alpha. So in the right triangle LFE, this angle equals to alpha according to our definition. This angle equals to 90 degrees. Therefore, this first angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in a triangle. In the next step, we'll extend the diameter EL by a straight line until it touches side CB of this rectangle ABCD. EL as a diameter, it is absolutely a straight line. When you extend the straight line by straight line, the result must be a straight line. Here we define the touching point of the extended diameter with the side CB. This point is point T. So we extended the straight line EL by straight line, therefore the result ET must be also a straight line. So by doing this construction, you're going to do the big quadrilateral ETBA. Inside the big quadrilateral ETBA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle. In total, they must be equal to 360 degrees according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside the big quadrilateral EFETBA, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be a rectangle if not a square. So in order to this big quadrilateral ETBA is a rectangle because it has 4 right angles. So write it down. Quadrilateral ETBA is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle ETBA, side ET must be equal to the opposite side AB. So write it down. In rectangle ATBA, side ET must be equal to the opposite side AB. But according to our definition, AB is the length of rectangle ABCD. So can I tell that AB is the length of rectangle ABCD? And from this equation, ET equals to AB equals to the length. We will derive that ET is also the length of rectangle ABCD. ET is the length of rectangle ABCD. So for me, I should find out that EL is the width of rectangle ABCD and ET is the length of rectangle ABCD. In the next step, we'll focus on the big right angle ETG. On the big right angle ETG, this angle equals to alpha, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. It's very easy to see that the big right triangle ETG is similar to this small right triangle ELF, according to angle, similarity rule. Anyway, I'll prove that those two right triangles are similar to each other. So, why those two right triangles? That is to say, the right small triangle ELF is similar to the right big triangle ETG. First of all, this is angle E. It is a common angle that belongs to both triangles. Angle E belongs to the small right triangle ELF, and angle E also belongs to the big right triangle ETG. So we can write down that angle A equals to itself. It's a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So in total, we found out that all the triangles of the big right triangle ETG are correspondingly equal to all the triangles of this right small triangle ELF, and therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. We actually found out that the big right triangle ETG is similar. This is the sign of similar to the right small triangle ELF according to angle similarity rule. And for the fact that those two right angles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side ET of the big right angle ETG over side EF of the small right angle ELF is equal to side EG of the big right angle ETG over side EL of the small right angle ELF. So if it again, from the fact that those two right angles are similar to each other, we derive that the following relationship exists between their sides. That side ET of the big right angle ETG over side EF of the small right angle ELF equals to side EG of the big right angle ETG over side EL of the small right angle ELF. ET is the missing side, so we leave it as it is, over EF. EF equals to 12 units in its length according to what is given as the question. And it is equals to EG. EG in total equals to 12 plus 10, that is 22. Over EL. EL is the missing side, so we leave it as it is. So in total, we actually found out that ET over 12 equals to 22 over EL. So here we'll cross multiply this equation and we get that ET times EL is equal to 22 times 12. So ET times EL is equal to 22 times 12. 22 times 12 is 264. So in total we found out that ET times EL equals to 264. But we already found out that ET is the length of rectangle ABCD and EL is the width. So we substitute ET in this equation by the length and we substitute EL by the width. Is equals to 264. So in total we found out that the length of rectangle ABCD times the width is equal to 264. The length times the width is of course the area of rectangle ABCD. So the area of rectangle ABCD that is the area that we are looking for in this question is equal to 264 square units. That is the answer to the first question. Repeat again, if we found out that the area of this rectangle ABCD is equal to 264 square units. So I finish with the first question. In the next step I will present to you the second question and we will solve the second question of this lecture. In the second question, our mission, our task is to find out the area of this trapezoid ABCD. It is given as the question that side AB of trapezoid ABCD equals to line segment AP. In addition, we know that line segment PD equals to side DC of trapezoid ABCD. This is line segment BQ, this equals to 4 units in its length. This is line segment QC, this equals to 9 units in its length. This is angle PQC, that is a right angle. Those two angles are also right angles. Again, our task is to find out the area of this trapezoid ABCD. So first of all, we know that according to what is given us the question, side AB is equal to line segment AP. So if we define the length of side AB as A, then the length of side AP must be also equal to A, because they are equal to each other according to what is given us the question. Likewise, it is given us the question that line segment PD equals to line segment DC. So if we define the length of this line segment PD as B, then the length of side DC must be also equal to B, because they are equal to each other according to what is given us the question. In the next step, we join points B and P together by a straight line. And we join points P and C together by a straight line. By joining points B and P, we get the right triangle APB, the right small triangle APB. AB equals to AP equals to A. So those two sides are equal to each other, and we have the rule that in front of equal sides in the triangle there are equal angles. So those two angles that are located in front of those two equal sides must be also equal to each other and their sizes. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha, because they are equal to each other according to the rule that I mentioned. We also know that the sum of the angles in any triangle, and especially in triangle APB, must be equal to 180 degrees. So which angles we have in the right small triangle APB? We have this angle that is the right angle, plus alpha that is plus 2 alpha. In total, the sum of those two angles must be equal to 180 degrees according to the rule that I mentioned. So 90 degrees plus 2 alpha equals to 180 degrees. Here we subtract 90 degrees from this equation, and finally we get that 2 alpha equals to 180 degrees minus 90 degrees, it is 90 degrees. So 2 alpha equals to 90 degrees. Here we divide this equation by 2. Finally we get that alpha equals to 90 degrees over 2, that is 45 degrees. So if we found out that this is angle alpha, that is equals to 45 degrees in its size. And this is also angle alpha, that is equals to 45 degrees in its size. This is the small right triangle APB. This small right triangle is also an isosceles triangle, because AP equals to AB. So we actually found out that in any right triangle that is also an isosceles triangle, we have one angle that is a right angle, and the two other angles must be equal to 45 degrees each of them. Therefore, this is the right triangle PDC. This is also an isosceles triangle, because PD equals to DC. So in this right and isosceles triangle, those two angles must be also equal to 45 degrees, each of them. You don't have to repeat on the same proof that those two angles are equal to 45 degrees. Because it is exactly the same proof. AD is one side of trapezoid ABCD, therefore it is absolutely a straight line. So if you focus on the right side of the straight line, AD is point P here, the sum of the angles must be equal to 180 degrees, according to rule 3 that says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the right side of the straight line, AD at point P? We have this angle that is 45 degrees, plus this angle that is 45 degrees, in total it is 90 degrees, plus this missing third angle, in total they must be equal to 180 degrees according to rule 3. Therefore this third missing angle, this is actually angle BPC, must be equal to 90 degrees in its size. Why? Because 90 degrees plus 45 degrees plus 45 degrees, in total it is 180 degrees. That is the sum of the angles on the right side of the straight line D at point P according to rule 3. Okay. We define this angle, that is actually angle QPC as alpha. What is the side of this missing angle? Angle BPQ. In total, the big angle BPQ is a right angle, it is equal to 90 degrees. So 90 degrees minus alpha is the side of this missing angle. 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, that is the size of the big angle BPC. Therefore, this missing angle must be equal to 90 degrees minus alpha. So, in the big right angle QPC, this angle equals to 90 degrees, this angle equals to alpha, therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. BC is one side of trapezoid ABCD, therefore it is absolutely a straight line. So if you focus on the left side of the straight line BC at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the left side of the straight line BC at point Q? We have this angle that is the right angle, plus this missing angle, in total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So, in the green right small triangle PQB, this angle equals to 90 degrees minus alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to alpha. Why? Because alpha plus 90 degrees minus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. It is very easy to see that the green small right triangle BPQ is similar to the big right triangle PQC, according to angle similarity rule. Anyway, I'll prove that those two right triangles are similar to each other. So why those two right triangles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, Those two angles are both equal to 90 degrees from solver, therefore they are equal to each other. So we can prove that all the triangles of the big right triangle PQC are correspondingly equal to all the triangles of this right small green triangle PBQ. Therefore, those two right triangles are similar to each other according to angle similarity rule. So I write it down. We actually prove that the right big triangle PQC is similar, this is the sign of similar, to the right small green triangle PBQ. And they are similar to each other according to angle similarity rule. And from the fact that those two rectangles are similar to each other, we will derive that the following relationship exists between their sides. But before that, it's very easy to see that PQ is a common side. PQ is a common side that belongs to both triangles. PQ belongs to the big small triangle PQB, and PQ also belongs to the big right triangle PQC. Okay? So, from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. That side PQ of the big right triangle PQC over side BQ of the small green triangle BQP is equal to side QC of the big right triangle PQC over side PB of the right green triangle PBQ. Over side PQ, over side PQ of the small right triangle PBQ. Repeat again. We derive that side PQ of the big right triangle PQC over side BQ of the small green triangle PBQ is equal to side QC of the big right triangle PQC over side PQ of the right green triangle PQB. Okay? So repeat again. From the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. The side PQ of the big right triangle PQC over side PQ of the small right triangle PQB is equal to side QC of the big right triangle PQC over side PQ of the small right triangle PQB. PQ is the missing side, so we leave it as it is. Over BQ. BQ is equal to 4 units in itself according to what is given as the question. And it is equal to QC. QC equals to 9 units in itself, also according to what is given as the question. Over PQ. PQ is the missing side, so we leave it as it is. So total, we actually found out that PQ over 4 equals to 9 over PQ. Here we will cross multiply this equation, and we will get that PQ times PQ is PQ squared is equal to 9 times 4 is 36. So PQ squared equals to 36. Here we will take a root out of this equation, and finally we get that PQ is equal to the square root of 36, that is 6. So PQ, the missing side PQ is equal to 6 units in its length. PQ equals to 6 units in its length. In the next step, we will implement the Pythagoras theorem on the big right triangle PBC. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is a version from Pythagoras theorem. So the hypotenuse in the big right triangle PBC is BC. Therefore, the square of the hypotenuse is BC squared. And it must be equal to PB squared plus PC squared. Repeat again, according to the Pythagoras theorem, in this big right triangle PBC, BC squared, that is the square of the hypotenuse, equals to PB squared plus PC squared. What is the length of BC? BC in total equals to 4 plus 9, that is 13. Therefore, BC squared is 13 squared, that is 169. And it is equal to PB squared. PB squared. So, in order to find out the value of PB squared, we will implement the Pythagoras theorem on this right small triangle APB. According to the Pythagoras theorem, in this right small triangle APB, a squared plus a squared equals to PB squared. So PB squared equals to a squared plus a squared, that is 2a squared. PB squared equals to 2a squared plus PC squared. In order to find out the value of PC squared, we will implement the Pythagoras theorem on this right triangle PDC. According to the Pythagoras theorem, in this right triangle PDC, b squared plus b squared equals to PC squared. So PC squared in total equals to b squared plus b squared, that is 2b squared. So PC squared equals to 2b squared. So in total we found out that 169 equals to 2 times a squared plus 2 times b squared. So 169 equals to, we take 2 out to second factor from those two expressions. So inside the brackets we left with a squared plus b squared. So in total we should find out that 169 equals to 2 times a squared plus b squared. Here we divide this equation by 2 and finally get that a squared plus b squared equals to 169 over 2. So in total we should find out that a squared plus b squared equals to 169 over 2. Our mission is to find out the area of this trapezoid ABCD. Actually, we have a special formula for the area of the trapezoid, but we will not use the special formula. We will find out the area of trapezoid ABCD in another way. Actually, the area of this trapezoid ABCD is equal to the sum of the areas of the three components the trapezoid ABCD consists of. Trapezoid ABCD consists this first component, that is the right small triangle ABP, and it also consists the second component, that is the big right triangle PBC, and the first component is the right triangle PDC. So the sum of the areas of those three components in total must be equal to the area of the trapezoid ABCD. So if you found out that the area of trapezoid ABCD equals to the area of this first component, that is the area of triangle ABP, plus the area of the second component, that it consists of, it is actually the area of the big triangle PBC, the big right triangle PBC, plus the area of the third component that the trapezoid ABC consists of, that is actually the area of the right triangle PDC. So in total, we actually found out that the area of trapezoid ABCD is equal to the sum of the areas of the three components that it consists of. The first component is the area of triangle ABP, and the second component is the right triangle PBC, so it is the area of the right triangle PBC. The third component is the right triangle PDC, so relate to the two components, the area of the third component, that is the area of the right triangle PDC. So we have to find out the area of each component separately, and then we relate the three areas together. This will get us the area, will give us the area of the trapezoid ABCD. So what is the area of the first component? That is actually the area of this small right triangle ABP. The area of any triangle equals to the base of the triangle times the height over 2. The base AB is A, the height AP is A. So the base times the height is A times A, that is A square over 2. So total the area of this small right triangle ABP is A square over 2. Plus the area of the second component that trapezoid ABCD consists of. The second component is the big right triangle PBC. And the area of this big right triangle PBC equals to the base of the triangle that is BC times the height that is QP over 2. Why the height is QP? Because of the fact that it creates 90 degrees with the base BC. Those two angles are right angles. So total the area of the big right triangle PBC equals to the base BC times the height QP over 2. Plus the area of the third component, that is actually triangle PDC. And the area of this triangle PDC is equals to the base of triangle PDC, that is DC, times the height DP over 2. The base DC is B, the height DP is also B, divided by 2. So it is B times B over 2. B times B is B square over 2. So in total the area of this third component, that is the right triangle PDC, is equal to B square over 2. A square over 2 plus B square over 2 is A square plus B square over 2 plus the area of the right big triangle PBC is equals to BC. BC in total is 4 plus 9, that is 13. Times QP. We already found out that QP equals to 6 divided by 2. So total the area of trapezoid ABCD equals to A square plus B square over 2 plus 13 times 6 over 2. 6 over 2 is 3, and 3 times 13 is 39. So in total this expression equals to 39. So she found out that the area of trapezoid ABCD equals to A square plus B square over 2 plus 39. But we already found out that A square plus B square equals to 169 over 2. Therefore, we solve A square plus B square here by 169 over 2. And we have to divide it by 2 again. Plus 39. So total the area of trapezoid ABCD equals to 169 over 2 times 2, that is 4, plus 39. So here we multiply 39 by 4 and then we divide it by 4 in order to overcome a factor with this number, and we get that in the numerator we will have 169 plus 39 times 4, that is 156, divided by 4. 169 plus 156 is 325 over 4. 325 over 4 is 81.25 square units. And that is the answer to the second question. So I should found out that the area of this trapezoid ABCD, that is the area that we are looking for in this question, it is equal to either 325 over 4 square units, or in terms of numbers, the area of this trapezoid ABCD is equal to 81.25 square units. So we finish with the second question. In the next step, summarize the lecture. We start with the first question, of course. In the first question, our mission, our task was to find out the area of this rectangle ABCD that blocks this circle. This circle is described by rectangle ABCD. It is given as the question that this is chord EF, that is equals to 12 units in itself. This is line segment FG, that is equals to 10 units in itself. Again, our mission is to find out the area of this rectangle ABCD. First of all, because of the fact that ABCD is a rectangle, all those 4 angles are right angles. And we know that the area of a rectangle equals to the length of the rectangle times the width. We define the length of this rectangle ABCD as AB, and the width is the SDA. Okay. The center of this circle is at point O. We join points O and N together by straight line. Point O is the center of the circle, point N is point on the circle itself, therefore ON is the radius of this circle. We define the radius of this circle as R, so ON equals to R. And because of the fact that the radius of ON is drawn to point N, that is the point of tendency of tangent AB with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. If AB is perpendicular to NO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and M together by straight line. OM is of course the radius of this circle, that is R. The radius OM is drawn to point M, that is the point of tendency of tangent DC with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius MO. If this is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, we join points O and D together by straight line. O is the radius of this circle, that is R. AD is tangent to the circle at point E. So, again, according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. By doing this construction, we can do here quadrilateral DMOE. Inside quadrilateral DMOE, we have 1, 2 free rectangles. The sum of free rectangles is 270 degrees. So 270 degrees plus the size of this 4 pieces again, in total they must be equal to 360 degrees. According to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this 4 pieces again must be equal to 90 degrees in its size. In the lower quadrilateral EONA, we have 1, two free right angles. Again, the sum of free right angles is 270 degrees. 270 degrees plus the size of this fourth angle in total must be equal to 360 degrees, and therefore this fourth angle must be equal to 90 degrees in size. So the big angle, the size of the big angle MON is 90 degrees plus 90 degrees, it is 180 degrees. The big angle MON is equal to 180 degrees in its size. And we know that any angle that is equal to 180 degrees in its size, it is defined as a straight line. Therefore, line segment MON is a straight line. If line segment MON is a straight line, then line segment MN is also a straight line. Line segment MON is a straight line, therefore line segment MN is also a straight line. So MN is a straight line that touches the circle at 2 points, M and N. Therefore MN is a chord. But MN is a chord that passes through point O, that is the center of the circle, and we know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore MN is the diameter of the circle. Okay? We found out that MN is the diameter of the circle. Okay? Anyway, MN is the diameter, it is of course a straight line. And therefore, this shape DMNA consists of 4 sides. 1, 2, 3, 4. And therefore, shape DMNA is a quadrilateral because it consists of 4 sides. But it is a quadrilateral with 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be a rectangle if not a square. So we went to the big quadrilateral DMNA, it's a rectangle because it has 4 right angles. But we also know that the opposite sides of rectangle are equal to each other. So in the big rectangle DMNA, side MN must be equal to the opposite side DA. Okay, again, in rectangle, the big rectangle DMNA, side MN must be equal to the opposite side DA. But the opposite side DA is the width of rectangle ABCD according to our definition. So we can write here that DA is the width of rectangle ABCD from one side, but actually we already found out that MN is the diameter of the circle. MN is the diameter of the circle. Here, we already found out that MN is the diameter of the circle. So, MN equals to DA, and DA is the width of rectangle ABCD according to our definition. And we have already found out that MN is the diameter of the circle. So we can write here that MN is the diameter of the circle. Okay. In the next step, we extended the radius EO by straight line until it touches the circle. We define the touching point of the extended radius EO with this circle. This point is point L. EO is the radius of the circle, therefore it is absolutely a straight line. When you extended the straight line EO by straight line, the result EL must be also a straight line. So EL is a straight line that touches the circle at 2 points E and L. Therefore, EL is a chord that passes through the center of the circle, that is to say, for this point, that is the center, point O, that is the center of the circle. And we know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore, EL is the diameter of the circle. So we can write that EL is the diameter of the circle. And so here we have found out that EL is the diameter of the circle, and from this long equation EL equals to the diameter equals to MN equals to AD equals to the width, we will derive that EL is the width of rectangle ABCD. Okay? EL is the width of rectangle ABCD. Anyway, we found out that EL is the diameter of the circle. So the next step, we join points L and F together with straight line. By joining points L and F, we can get here triangle LFE. Triangle LFE subtend on EL, that is the diameter of the circle. As we know, the any triangle that subtend on the diameter of the circle must be equal to 90 degrees in its size according to rule 7. Therefore, triangle LFE is equal to 90 degrees according to rule 7. So, in the right triangle ELF, we define this angle as alpha. This angle equals to 90 degrees according to rule 7. Therefore, this perpendicular angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees, which is the sum of the angles in any triangle. In the next step, we extended the diameter EL by straight line until it touches side CB at this point. So we define the touching point of the extended diameter EL with side CB. This point is point T. So EL is the diameter of the straight line, and we extend the straight line by straight line. The result ET must be also a straight line. So ET is the straight line. So by doing this construction, we can do quadrangle ETBA. Instead of quadrangle ETBA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4-piece angle, in total it must be equal to 360 degrees. According to the rule that says that the sum of the angles in any quadrangle is equal to 360 degrees. Therefore, this 4-piece angle must be equal to 90 degrees in its size. So inside the big quadrangle ETBA, we have 4 right angles. And according to rule 5, any quadrangle that has 4 right angles must be a rectangle if not a square. So we let to quadrangle ETBA is a rectangle because it has 4 rectangles. But we also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle ETBA, side ET must be equal to the opposite side AB. Again, in the big rectangle ETBA, side ET must be equal to the opposite side AB. But AB itself is the length of rectangle ABCD. So we can write here that AB is the length of rectangle ABCD. And from this equation, ET equals to AB equals to the length. We will derive that ET is also the length of rectangle ABCD. So in total, we found out that EL is the width of rectangle ABCD and ET is the length of rectangle ABCD. Okay. In the next step, we focused on the right big triangle ETG. On the right big triangle ETG, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this first angle must be equal to 90 degrees minus alpha. To 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. So it is very easy to see that the small right triangle ELF is similar to the big right triangle ETG. So why those two right triangles are similar to each other? First of all, this is angle E, that is a common angle that belongs to both triangles. Angle E belongs to the small right triangle ELF, and angle E, of course, belongs to the big right triangle ETG. Therefore, we can write out that angle E equals to itself as a common angle that belongs to both angles. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we found out that all the triangles of the big right triangle ETG are correspondingly equal to all the triangles of the right small triangle ELF. And therefore, those two right triangles are similar to each other according to angle similarity rule. So again, if we found out that the big right triangle ETG is similar, this is the sign of similar, to the right small triangle ELF according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side ET of the big right triangle ETG over side EF of the small right triangle EFL is equal to side EG of the big right triangle ETG over side EL of the small right triangle ELF. So again, from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. That side ET of the big right triangle ETG over side EF of the small right triangle ELF is equal to side EG of the big right triangle ETG over side EL of the right small triangle ELF. ET is the missing side, so we leave this it is over EF. EF equals to 12 units in itself, according to what is given as the question, and it is equals to EG. EG in total equals to 12 plus 10, that is 22, over EL. EL is the missing side, so we leave this it is. So in total, we actually found out that ET over 12 equals to 22 over EL. Here we cross multiply this equation, and finally found out that ET times EL equals to 22 times 12. So ET times EL equals to 22 times 12. 22 times 12 is 264. So in total, we should find out that ET times EL equals to 264. But we have already found out that ET is the length of rectangle ABCD and EL is the width. So we solved ET by the length and EL by the width. So in total we actually found out that the length of rectangle ABCD times the width is equal to 264. What is the length times the width? It is actually the area of rectangle ABCD. So we found out that the area of rectangle ABCD, that is the area that we are looking for this question, is equal to 264 square units. The area of this rectangle ABCD is equal to 200 square units. Okay, so we finished with the first question. In the next step, I'll present to you the second question and solve the second question of this lecture. In the second question, our mission is to find out the area of this trapezoid ABCD. So in the drawing, we have trapezoid ABCD, and we also know that side AB of trapezoid ABCD is equals to line segment AP. In addition, we know that line segment PD equals to side DC of line segment PD equals to side DC of trapezoid ABCD. We also know that this is line segment BQ, that is equals to 4 units in its length. This is line segment QC, that is equals to 9 units in its length. This is again QPC, that is this is again PQC, that is a right angle. Those two angles are also right angles. Again, our mission is to find out the area of this trapezoid ABCD. So we know that AB equals to AP according to what is given as the question. So if we define the length of AB as A, then the length of AP must be also equal to A because they are equal to each other according to what is given as the question. Likewise, it is given as the question that PD equals to DC. So if we define the length of PD as B, then the length of side DC must be also equal to B because they are equal to each other according to what is given as the question. In the next step, we join points B and P together by side line. We join points B and C together by side line. By joining points B and P, we get the right small triangle ABP. And in the right small triangle, those two sides are equal to each other. And we have the rule that in front of equal sides, there are equal angles. So those two angles that are located in front of those two equal sides must be also equal to each other in their sizes. So if the size of this angle is alpha, then the size of this angle must be also equal to alpha because they must be equal to each other. We also note that the sum of the angles in any triangle, and especially in the right small triangle ABP, must be equal to 180 degrees. So which angles we have in the right small triangle ABP? We have this angle that is 90 degrees. Plus angle alpha, that is 2 alpha, so 90 in the right triangle ABP, 90 degrees plus 2 alpha must be equal to 180 degrees according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Here we subtract the 90 degrees from this equation, and finally found out that 2 alpha equals to 180 degrees minus 90 degrees, it is 90 degrees. So 2 alpha equals to 90 degrees. Here we divided this equation by 2 and finally found out that alpha equals to 90 degrees over 2, that is 45 degrees. So this is angle alpha, this is equals to 45 degrees in its size, and this is also angle alpha, this is equals to 45 degrees in its size. So this is a right and isosceles triangle, and in a right and isosceles triangle, we have one angle that is a right angle, and the two other angles, each of them must be equal to 45 degrees in their sizes, and the right triangle PDC is also a right triangle and also associated triangle because PD equals to DC. So we have one right angle and the two other angles must be equal to 45 degrees and the sizes each of them. Okay? So if you focus on the right side of the straight line, AD is one side of trapezoid ABCD, therefore it is absolutely a straight line. So if you focus on the right side of the straight line AD at point P here, the sum of the angles must be equal to 180 degrees according to rule 3 that says that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the right side of the straight line AD at point P? Point P we have 45 degrees plus 45 degrees, that is 90 degrees, plus the size of this first missing angle in total must be equal to 180 degrees according to all three. Therefore this first missing angle must be equal to 90 degrees inside. Why? Because 90 degrees plus 45 degrees plus 45 degrees, in total it is 180 degrees. It is the sum of the angles on the right side of the straight line AD at point P according to all three. So this missing angle PBC must be equal to 90 degrees in its size. We define the size of this angle QPC as alpha. So angle alpha plus this missing angle in total must be equal to the big angle BPC, that is the right angle. Therefore this missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees. That is the size of the big angle BPC. So this missing angle must be equal to 90 degrees minus alpha. In the right angle QPC, this angle equals to alpha, this angle equals to 90 degrees minus alpha. Therefore this first missing angle, this angle equals to alpha, this angle equals to 90 degrees. Therefore this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. If you focus on BC is one side of the trapezoid ABCD, therefore it is absolutely a straight line. So if you focus on the left side of the straight line BC at point Q here, the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the left side of the straight line BC at point Q? We have this angle that is 90 degrees, plus this missing angle, in total the sum of those two angles must be equal to 180 degrees according to all three. Therefore this missing angle must be equal to 90 degrees in size. So in the right small green triangle BPQ, this angle equals to 90 degrees minus alpha, this angle equals to 90 degrees, therefore this first missing angle must be equal to alpha. Why? Because alpha plus 90 degrees minus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in a triangle. It's very easy to see that the small right triangle PBQ, the small green right triangle PBQ is similar to the big right triangle PQC according to angle similarity rule. So anyway, I'll show why those two right triangles are similar to each other. First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, both angles are equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So I can prove that all the three angles of the big right triangle PQC are correspondingly equal to all the three angles of the right small triangle, green triangle PQB. Therefore those two right triangles are similar to each other according to angle similarity rule. So again, I can prove that the big right triangle PQC is similar to the small right triangle PBQ according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side PQ of the big right triangle PQC over side BQ of the small green triangle PBQ is equal to side QC of the big right triangle PQC over side PQ of the small right green triangle PBQ. Repeat again. From the fact that those two right triangles are similar to each other, we derive that side PQ of the big right triangle PQC over side BQ of the small right triangle PBQ is equal to side QC of the big right triangle PQC over side PQ of the small right triangle PBQ. PQ is the missing side of unity cities over BQ. BQ equals to 4 units in its length, and it is equals to QC. QC is 9 units. Over PQ, PQ is the missing side, so unity cities. So in total we should found out that PQ over 4 equals to 9 over PQ. Here of course multiply this equation and finally found out that PQ times PQ is PQ square equals to 9 times 4, that is 36. So PQ square equals to 36. We took out this equation and found out that PQ equals to the square root of 36, that is 6. In the next step, we implemented the Pythagoras theorem on the right big triangle CBP. According to the Pythagoras theorem, in this right big triangle CBP, BC squared, that is the square of the hypotenuse, equals to BP squared plus PC squared. And again, the big right triangle PBC, according to the Pythagoras theorem, BC squared, that is the square of the hypotenuse, equals to PB squared plus PC squared. BC in total equals to 4 plus 9, that is 13, therefore BC squared is 13 squared, that is 169, and again BC squared is 169, and it is equals to BP squared. What is the value of BP squared? In order to find out the value of PB squared, we will implement the Pythagoras theorem on the right small triangle APB. According to the Pythagoras theorem on the right small triangle APB, A squared plus A squared equals to PB squared. So PB squared in total equals to A squared plus A squared, that is 2A squared. So PB squared is 2A squared plus PC squared. What is the value of PC squared? In order to find out the value of PC squared, we implement the Pythagoras theorem on the right triangle PDC. According to the Pythagoras theorem on the right triangle PDC, B squared plus B squared equals to PC squared. So PC squared equals to, in total, to B squared plus B squared, that is 2B squared. So PC squared equals to 2B squared. So in total, we found out that 169 equals to 2A squared plus 2B squared. Here we took out a common factor of 2 from out of those two expressions. So in total, we found out that 169 is equal to 2. Inside the brackets, we have A squared plus B squared. So in total, 169 equals to 2 times A squared plus B squared. Here we divided this equation by 2 and finally found out that A squared plus B squared equals to 169 over 2. Our mission is to find out the area of this trapezoid ABCD. The area of trapezoid ABCD is equal to the sum of the areas of the 3 components that it consists of. Triangle trapezoid ABCD consists, the first component that it consists of is the right small triangle ABP, the second component is the right B triangle PBC, and the third component the trapezoid ABCD consists of is the right triangle PDC. So the sum of the areas of those 3 components in total must be equal to the area of trapezoid ABCD. So again, the area of trapezoid ABCD is equal to the sum of the areas of the 3 components that it consists of. That is to say, the first component is triangle ABP, therefore it is the area of triangle ABP. The second component is the big right triangle PBC, so it is plus the area of the big right triangle PBC. And the third component is the right triangle PDC, therefore it is plus the area of the right triangle PDC. So we have to find out the area of each component and the sum of the areas of those 3 components. In total, it will be equal to the area of trapezoid ABCD. That is the area that we are looking for in this question. So the first component is the area is the right triangle ABP. So what is the area of this right triangle ABP? It is equal to the base AB times the height over 2. The base AB is 8, the height AP is 8. So it is 8 times A over 2. 8 times A over 2 is A squared over 2. So the area of the first component is A squared over 2. Plus the area of the second component, that is the big triangle PBC. The area of any triangle equals to the base times the height over 2. The base is BC, the height is QP over 2. So in total, the area of the big triangle PBC equals to the base BC times the height QP over 2. Plus the area of the third component, that is the area of the right triangle PDC. The area of the right triangle PDC equals to the base DC times the height DP over 2. DC is B, DP is also B, so it is B times B, that is B squared over 2. So in total, the area of this triangle PDC is equal to B squared over 2. A squared over 2 plus B squared over 2 is A squared plus B squared over 2. BC is 13, QP is 6 divided by 2. So in total, the area of the big triangle PBC is equal to 13 times 6 over 2. So in total the area of trapezoid ABCD equals to a squared plus b squared over 2. And here, what is the value of this expression? It is 6 over 2 is 3, and 3 times 13 is 39. So in total the value of this expression is 39. So the area of trapezoid ABCD equals to a squared plus b squared over 2 plus 39. But we already found out that a squared plus b squared equals to 169 over 2. Therefore, we substitute a squared plus b squared here by 169 over 2, and we have to divide it by 2 here. So in total, this expression will be equal to 169 over 2 times 2 plus 39. So it is 169 over 2 times 2, that is 4. So it is 169 over 4 plus 39. Here we multiply 39 by 4, and then we divided it by 4 in order to account factor with this number. So in total, the numerator will have, after multiplied it by 4 and then divided by 4, the numerator will have 169 plus 4 times 39, this is 156 over 4. 169 plus 156 is 325 over 4. 325 over 4 is 81.25 square meters. So in total, we found out that the area of this trapezoid ABCD is equal to either 325 over 4 square meters, so in terms of numbers, the area of this trapezoid ABCD is equal to 81.25 square meters. Okay, thank you very much.